This is Module 10, Lesson 4. We're going to look at physical states in chemical reactions. What that means is we are going to attempt to put after each thing in a reaction, whether it is a solid, a liquid, a gas, or aqueous. So here are the four, I refer to them as physical states that you could have. The simplest thing to do is honestly just memorize these four things. The least amount to memorize would be to work on liquids and gases. There are two liquids on the periodic table. That would be mercury and bromine. And then water is your other common liquid when it's not in combustion reactions. Because when water is heated up in a combustion reaction, it comes out as a gas. The gases are the Inkelhoff part of Brinkelhoff. So remember we've got Brinkelhoff right here. So if you just take this section right here, Inkelhoff, those are gases: nitrogen, chlorine, hydrogen, oxygen, and fluorine. Of course, if you had a noble gas in a reaction, well, it's a noble gas, it's a gas, and then water and combustion reactions. Everything else that we have should fall either as an element that would be a solid or an ionic compound. Most of the time that will be either aqueous or a solid if it doesn't. Remember what we learned about ionic compounds back in Module 6. Ionic compounds are solids at room temperature unless they'll dissolve in water, in which case we call them aqueous. That's exactly what aqueous means, is dissolved in water. So how do you figure out if an ionic compound will dissolve in water or not? We use these solubility rules. It's for page 6 of your reference table. So if you go to your reference table, if I can write that up here, page 6, you'll see this little set of solubility rules. So what you do is you identify it by the end. So for example, if we have a compound like NaCl, we always look at the most thing. The right ending of this is chloride, so we find chlorides over here, and you'll see them right there. All chlorides fall under the soluble category. If they're soluble, you're going to put AQ after it. And if they're insoluble, you'll put a solid. So all chlorides are soluble, all bromides and all iodides, and then there's an except silver chloride, lead chloride, or mercury 1 chloride. Well, we look at who it's with sodium. Sodium's not one of the exceptions, so that means that sodium chloride would be aqueous. Okay. If it happens to be an exception, like if we had silver chloride, then chlorides are soluble unless they're with silver, lead, or mercury. So since it's with one of the exceptions here, it's with silver, that's going to make it become insoluble. The same thing happens if you're over here. So for example, all carbonates are soluble except group 1A. Well, how do you know what's group 1A? You look at the reference table and you'll see the group labels numbered. So up at the very top, if it was something like Na2CO3, that's sodium carbonate. Carbonates are not soluble. That means they're solids unless it's with a group 1A element. Well, sodium is a group 1A element, so that means that would be aqueous. Okay, so all we do is we just follow this chart. It's nothing that you have to memorize. The only thing that you need to memorize is that when you have an ionic compound, you come look at this little table. Okay. The other thing that I've done is try to give you some ideas about the reactions and what you would do. Now, I'm not doing this as like an every case scenario, but what I'm doing is we're going to work underneath these understandings, which means if you're going to Google answers to quiz and test questions, and I'm asking you to do this in a particular way based on what you're taught, then you may very well put down an answer that I'm not expecting based on the rules that I'm giving you, and you're going to miss the question. So in general, with synthesis reactions, you just follow all these rules we just did on this page right here. Decomposition is often a solid substance that's heated. And if that's the case, I don't care what the substance is. So I'll try to give you an example up here. Like if we have NaCl and it decomposes into chlorine. Well, based on what I was telling you before, like we just looked at it over here, NaCl would be aqueous. But because this is being decomposed, how you get salt to decompose is basically you would have to heat it up to the point that it either fell apart. Certain things you can electrocute until they fall apart. Like this would not be something that you would dissolve in water in order to get it to break up into sodium and chlorine. So what we would label this as is solid sodium chloride. Solid sodium because it is a metal element off of the periodic table. And then we just said over here that chlorine is going to be a gas because it's part off. That's a Q though. So we would put G for gas, okay? And so, oftentimes with decomp, we're not going to have anything that's aqueous. It can sometimes be a liquid that decomposes. So if you happen to know that a particular substance was a, like happened to be a liquid, like for example, you can decompose water into hydrogen gas and oxygen gas by electrocuting it. And so like I know that water is a liquid. It's not at an extreme temperature. And then when we electrocute it, we'll actually separate into gaseous hydrogen and gaseous oxygen. And I know they're gases because they're a part of alcohol. Okay. Single and double replacement. This is going to be aqueous territory. The way that I like to think of these is like what you need to do with those is get them to make something new. And I think of it kind of like Legos. So for a very crude drawing here, like if I have Legos together, if I have these three things of Legos right here where I've got like 3 Legos put together and I want to put them together in some other way, the first thing that I'm going to have to do is pull them all apart so that they're no longer together so that I can do something with them. And how we get them to come apart is we put them in water. So we have like a beaker and we put chunks of NaCl down inside of here in the water. What happens when they go in the water is they ionize. Like the NAs split up into Na pluses, the Cls make Cl minuses, and they start floating around solution. And when they start floating around in solution like this, then what that means is we could put them together with something else. It's kind of like taking apart the Lego so that we could make something new. So when you get to single and double replacement, that's all about the dissolve. Combustion. It doesn't matter what you put for the hydrocarbon. So for example, with these, and give an example over here. So for example, with those, like if you have a combustion equation, you're going to have C something and H something plus oxygen makes CO2 plus H2O because that's just our description of a combustion reaction. I could really care less what you put for this because in the practice problems you have some of these. It's fair game to me. So in the parentheses, I don't care if you just put a question mark because it's kind of up for debate. You would have to know a lot more about what your substance is before you could know. But what you can know and what I want you to know for our test is that oxygen has to be a gas, carbon dioxide is a gas, and the water will be a gas. Now, why will water be a gas this time instead of a liquid like up here? Because, well, it's burning, it's fire. You've seen candles burn. You've seen other stuff, like you've seen gas logs or a fireplace or, whatever. You've never seen liquid water coming out of that because it's such a high temperature, it'll be like steam, gaseous water. So everything else, this is the part that I care about you knowing in a combustion reaction is all of the rest of the stuff. I really don't care what you put for this. I'll accept anything. So with that being said, let's just look at several examples. And what I expect you to do with this, if you think you've got the hang of it and you want to skip ahead a little bit and fast forward through the rest of this, like once we do a couple of examples, then by all means, feel free to go ahead. If you're not sure, then you can watch this more than once. What I do care about is that you get it right. So here's our first example. And just to make it easier on us, I put the solubility rules at the bottom. Well, here's what I noticed. It's a double replacement reaction because I see compounds on both, 2 compounds on both sides. So what that tells me is I do need to use the solubility rules here. And remember, we're going by the thing on the right. Well, this is phosphate. It's in 2 of these. So looking it up one time will get us 2 answers. So I see phosphate phosphates right here. Phosphates are insoluble unless they're with group 1A or ammonium. Well, then the question is who is sodium and who is silver? Sodium is a group 1A element, so that means that this will then become aqueous. And silver is not a group 1A. Silver is a B element. It's a transition metal, so it's not one of the exceptions, so it stays on the insoluble side. So it's a solid. Okay, what about these two? These are nitrates. If you're not sure, you have this in your periodic table, you could look it up. All nitrates are right here, and there's not a single exception. Anything with nitrate in it is soluble in water. So we'll put AQ and AQ for aqueous and aqueous. Here's our next example. Okay, we look at it again. So what I see is what appears to me to be a kind of a double replacement reaction. It looks kind of like it is because I see compounds on all sides. It's not a true double replacement, but you could go ahead and operate under the idea of it's not synthesis, it's not decomp, it's not combustion. So just you go ahead with the solubility rules down here. This first thing is it ends in a hydroxide. So hydroxides are right here. Hydroxides are not soluble except when they're with group 1A, strontium, barium. Look at what this is. This is barium. Barium and ammonium. So since it's with barium, that flips it over to the other side. So that will be S. What about carbon dioxide? Well, we should know at this level, most of you've had biology, that carbon dioxide is a gas. You're breathing it out with every breath that you exhale. I don't know why I'm getting ready to put aqueous there. That's a G for gas. So that's going to be gaseous. If you mix those two things together, then it makes barium carbonate. Well, it's an ionic substance. Carbonates fall here. They're insoluble unless they're with group 1A or ammonium. Well, barium is in group 2A. If you look at the reference table, you'll see it under group 2, which means that it stays insoluble. So we put an S for solid. And then our H2O. Well, y'all, it's water. Think about it. Is this happening at high temperatures? Not to our knowledge. It's not combustion. It's not a decomposition. So best guess would be that it would be happening as a liquid, which there was water present over here to make this aqueous, except the water just wasn't doing anything in the equation. It is actually going to make water on the outside coming out of it. All right, here's this one. Now this is a true double replacement reaction. I see compounds all the way across. This first thing is sodium hydroxide. Hydroxides are insoluble. Group 1A makes it become soluble. Well, sodium's group 1A, so they become aqueous. HCl. This ends in chloride, and this ends in chloride. Well, all the chlorides are soluble unless it's silver, lead, or mercury. Well, it's with hydrogen and sodium. That's none of the exceptions. So we're going to put aqueous and aqueous. And now here we have our good friend water once again. Well, water is it's most commonly found as a liquid. This is not at high temperatures. It's not a combustion, so we're going to put an L for liquid. Okay. All right. This is a single replacement. How do I know? I see single element, compound, single element. So look at zinc. It's not a compound. When you have elements, we base it off of what we know. We know that there's two liquid elements. We have mercury and bromine. This is neither one of those, so solid. This is not mercury or bromine, so solid. Copper and zinc are metals. Metals are solids. What about these two? They're sulfates. Well, when we come down here, just kidding, sulfates are on this side. The sulfate are soluble, except calcium, strontium, barium, mercury, lead 2, or silver. These are not with any of those exceptions, so this would be aqueous and aqueous. There we go. Okay. Another single replacement. So since it's single replacement, I know that anything that is an ionic compound will be checked by the solubility rules down here. This first thing is just metal. It is just pure calcium. And pure calcium is a metal. Hello, dogs. So this is going to be a solid. This is our good buddy water. Since it's not a combustion reaction and it's nothing that we know of that's happening at high temperatures, we're going to put an L for liquid. This needs to be checked based on our table. This is a hydroxide. So a hydroxide is going to be here. And so the hydroxide is going to be, oops, that's a highlighter. The hydroxides are going to be insoluble unless it is with a group 1A, strontium, barium, or ammonium. Well, calcium, if you look on your table, sorry for the dog interruption, is in group 2A. And so it is not going to be one of our exceptions. It's going to stay over here in insoluble, which means that'll be solid. And hydrogen, what do we do with it? Well, it's part of Ingelhoff because it's elemental, so we're going to put G for gas. Okay, let's see if we can do a couple more without child interruptions. The dog is going to make itself heard. Okay, this one, I see a decomposition reaction. So what this tells me is that, you know, one of two things. I can go under the assumption that this is going to be possibly a solid, but what we don't want to do is go, oh, okay, let's just do everything by the solubility rules. Okay, so I put it on here, but this is to be a case where we're not going to look, because based on how I want you to do this is just assume that like single and double replacements need to have the solubility rules checked. But for decomposition, synthesis, and combustion, it's going to be a no. So you can think of this as an ionic compound that basically, you know, if you have it, ionic compounds are solids at room temperature. If you decompose it, then it would give you water and carbon dioxide. Well, if this is occurring at high heat, you know, most likely if you're heating this up, this would come out as a gas, and carbon dioxide is always going to be a gas. So it's fair to assume that it could be this. Now, I'm not going to be steering you correct in every single circumstance with this, but good enough to suit our purposes. So I'm just asking you to operate by this. What about this one? I recognize this is a combustion reaction. I see the C and the H. I've got the oxygen, the carbon dioxide, and the water. I don't need the solubility rules. I told you at the beginning I could care less what you put for this one. You would have to know more about it. There is a correct answer to it, but you would have to know what it is, and we don't do that at our level. So you could, you know, put whatever, solid, liquid, gas, pick one. The rest of these, though, I count on that they would be gas, gas, and gas. What about this one? Well, what I see here is a double replacement reaction. I see two compounds, which means I do need to be using the solubility rules. I have a hydroxide right here, and I did this. We're going to see more of this from me in the next lesson. Another way to look at HOH is H2O. So this is water. We're not going to look at it. You could look at it under the hydroxides. Heck, let's just go ahead and do that. Let's pretend like here we have hydroxide. So here's calcium hydroxide and here's hydrogen hydroxide. So we've got calcium hydroxide. Hydroxides are not soluble unless it's with one of these exceptions. Calcium is not one of those, so it's going to be solid. Well, hydrogen is in a group 1A, which means that it would be soluble, except we need to recognize it as water because we don't want to put aqueous. It's not dissolved in water. It is water, like it is liquid water. Sulfates, they're down here. Hydrogen's not an exception. Calcium is not. Oh, calcium is an exception right here. So this one's going to be aqueous, and this one's going to be solid because it's one of our exceptions. Here is another double replacement reaction. So we do need to check this down here at the bottom. We have two nitrates up here. Let's see. So all nitrates are soluble. There are no exceptions. So aqueous and aqueous. This one, we have two carbonates. Carbonates are not unless they're with group 1 or ammonium. And ammonium, if you look on your reference, the polyatomic ion NH4. This is a group 1A element, which turns it into soluble. This is a group 2A element, which keeps it at insoluble. So we have aqueous, aqueous, soluble, aqueous. All right, we have another single replacement, which means I do need to be checking my solubility rules. For all the compounds, this is a metal, so it's a solid. This is it's an element, it's elemental hydrogen, which means that it's part of Inkelhoff. I recognize that as being a gas. These two are sulfates. The sulfates are here. Neither one of these is an exception, so that would be aqueous and aqueous. All right, here we have another decomp reaction. This is the only thing that's on the left-hand side. So we're going to assume that this is at, that you're going to have to heat this up to make it decompose. And as such, we are not checking the solubility rules. This would be a solid because it's an ionic compound. We would put a solid here because it's an ionic compound. And, for what I'm asking you to do, oops, I put gas, but I meant to put liquid. We're going to put liquid because we're heating this up, which would most likely make this come out as a, no, I had it right the first time. I'm talking myself in and out of things. I'm listening to kids in the background. And so since it's at higher heat, we'll put G for gas. Okay. So what you need to do now is you have a practice sheet for this where on your practice sheet, like your first example is like this. It's got into and it's got brackets. It's got the parentheses plus blank to blank into O5 and more. So, okay, let me explain in case you don't read my instructions. This is completely optional. As you might figure, this is used to balance it. If you would like some extra balancing practice, you can use these blanks to do it. What is not optional is you have to do the parentheses. Okay, that is mandatory. There are quite a few covalent compounds on this. And so whenever, on a lot of them, whenever you have like combustion reactions or you have this is not an ionic compound. I've tried to give you some information on my answer key. Like, I don't care what you put for this. I really don't, simply because, you don't really have a way of knowing. And I've indicated that to you on the answer sheet. So if you get to this and you go, I don't know, am I supposed to know this or not? You can send me a message. And you could say, Houston, I have a problem. It certainly wouldn't be the first time I've ever heard that. And ask me, like, am I supposed to know this one? And I can say, no, there's a few of them that you shouldn't know, and they're covalent things. But most of the things that you should be able to deal with. This is something that in class students often want to ask questions about. So I'm quite frankly going to be surprised if you don't ask anything. I hope to see you at office hours. And if my office hours don't fit for you, then give me a message and tell me what would work for you. Good luck with practice.